first thing we're going to talk about here is specific heat capacity. Temperature, so the average kinetic energy of the particles of a substance. So as we know, temperature affects how fast particles move, okay? And they have a certain energy that's associated with them, okay? Any change in temperature can be used, about basically delta T here, of course. My writing's not very good either, by the way. Any delta T, or any change in temperature, right? So any change in temperature used to determine whether a system has absorbed or released energy, okay? In some cases, it gives off energy. In some cases, it takes in energy, right? We know those usually, and when we talk about reactions, we usually think about endothermic and exothermic reactions, right? Different substances need to absorb or release different amounts of energy as they heat up or cool down. So, for example, if we had a piece of aluminum, it's not going to heat up or cool down at the same rate as a piece of tin, for example, or a piece of copper, okay? So we need to know, basically, we're going to look at what those different heats are, basically. That's what we're going to look at in the first lesson here. We talk about what we call the specific heat capacity, and that is the amount of energy that's required, okay? So how much energy is required to heat up 1 gram of a substance. Like I said, could be different substances, right? But a gram of a substance by 1 degree Celsius, okay? So how much energy does it require to heat up a piece of aluminum? A gram of aluminum is different than the amount of energy required to heat up a gram of copper, for example, okay? That's not the same amount of energy you need to put in there, or a gram of water for that matter, okay? The units for specific heat capacity are in joules per gram degree Celsius. Joules per gram degree Celsius are the units we're going to use here. Each substance has a unique specific heat capacity value. Those values are going to be in your data booklet, so let's get those out. You'll find them on the second page, I believe. And they should be in the top right corner on the second page there, kind of thing, as you open up. So it tells you there, okay, on the top right there, basically, some specific heat capacities, okay? And specific heat capacities, you can look there, for example, to heat up, for example, the third one down, copper. It takes 0.385 joules of energy, basically, for every gram that you would have of that substance, okay, to heat it up 1 degree Celsius, all right? If you looked at aluminum, it would take 0.897 joules to heat up or cool down for every gram degree Celsius, okay? Substances with a smaller specific heat capacity tend to heat up or cool down more quickly, right? A smaller amount of energy is required, so they tend to get, heat up quicker or cool down faster. The formula for this is Q equals MC delta T, okay? This is actually going back to Science 10 a little bit here, okay? Now, this is obviously going to be the mass of the substance that you have. Okay, I give you guys the notes. Obviously, I expect you guys to copy down some stuff as well. This here is the specific heat capacity that's going to be required, that goes with that substance, whatever it happens to be. If it's aluminum, you'd look up the aluminum number. If it's water, you'd look up the water number, et cetera, et cetera. Okay, the units to go with this here, of course, are joules per gram degree Celsius. Okay, so joules over grams and Celsius, basically. This here is what we call the temperature change. So change in temperature. And the units to go with this are in actually degrees Celsius. And finally, this is the energy. the energy that's required. Okay? And the energy is measured in what we call joules, or basically just the J. Okay? So that's going to be measured in joules. I'm also going to give you some other units as well. And the reason I do this is because the other units are actually a little bit more useful, because usually, I would say 95% of the time, we're going to actually use the other units to go with this as well. The other units that we can have here are kilograms. Okay? So you might be talking about something that's obviously we're talking in terms of kilograms. Well, okay, if we have kilograms here, right? If you think about units, as far as units go, look, the grams and the grams up here, just look at the red part. Grams and grams would cancel, yes? The Celsius and the Celsius would cancel because the Celsius is on the bottom, right? And the Celsius is on the top. Those would cancel. What are you left with? You're left with joules, okay? And that's what Q is, joules, energy, right? If you put kilograms here, well, the grams and the grams would cancel, the Celsius and the Celsius would cancel, but really what you're left over with then is if you're going to make it 1,000 times bigger, your energy that's you're going to get from that is going to be 1,000 times bigger. So we're going to put kilojoules here, okay? So you can also use those units as well, okay? And I'm going to tell you right now, it really depends on the question, but in most cases, we're going to be using the blue stuff, okay? And of course, this is still going to be in joules per gram degree Celsius, okay? And this is still degrees Celsius there. Like I said, the Celsius is going to cancel because this is on the bottom, top. Grams will cancel, and you're going to be left with kilojoules as an answer, okay? So if you're using kilograms, just remember you're getting kilojoules as an answer. If you're using grams, you get joules. Okay? So grams and joules, kilograms, kilojoules go together. Okay? It doesn't matter which one you use, it depends on the question that you're going to be using it in. And of course, how are we going to figure out delta T, the change in temperature? Well, if we're heating something up, that's the initial temperature. Maybe we start at 20 degrees Celsius, maybe we heat it up to 40 degrees Celsius. Okay? So this is, of course, your final temperature here. This would be your initial temperature. And by the way, these are both in degrees Celsius. Okay? And of course, the temperature change. How much did it change by? Well, if you start at 20 and you go up to 40, that's a change of 20, right? So this would be your change in temperature here. Okay? We'll show you some examples of this in a little bit here. All right? So, H2O, by the way, water, has a density of 1 gram per milliliter. So for every milliliter of water, that's equivalent to a gram. Okay? If you had, for example, 500 milliliters of water, every milliliter is a gram of water. You can weigh that out. Okay? How do you do that? Well, you would take a beaker, for example, weigh it empty, okay, or tear out the scale, zero it, and you would measure out 500 milliliters, put it into the beaker, and you would see it weighs 500 grams. 500 milliliters, 500 grams, has a density of 1 gram for every milliliter, okay? So when they talk about milliliters in questions, quite often we're going to be talking about grams in the formula, okay? If you look back at here, where do you see milliliters in this equation here? You don't. Okay, you see grams, you see kilograms, perhaps. So we're going to change the 500 milliliters, we're going to change it to 500 grams. Okay? Likewise, if we're talking about milliliters, we could also talk about liters, right? If we're talking about liters, 32 liters, remember, is really 32,000 milliliters, right? Well, 32,000 milliliters would be 32,000 grams, right? 32,000 milliliters, 32,000 grams. Well, can we change that to kilograms? Sure. 32 liters would be 32 kilograms, yes? So those two go together. And that's why you should really know the different units that are associated with them. So if we're talking about liters, you probably want to use kilograms. If we're talking about grams, think about milliliters, okay? So, specific heat capacity of H2O is reported as 4.19 joules per gram degrees Celsius. That's on, of course, that is in your data booklet as well, okay? So, let's get to our first example here, and I'll show you some of these, and maybe it'll make a little more sense to you. Calculate how much heat in kilojoules must be absorbed to heat up 750 milliliters of water from 15.2 to 45.8. Okay? So we're going to look at our formula here. How much heat in kilojoules? Well, okay, let's start with this here. Let's fill in some of the things we know. First of all, what are we looking for? How much heat in kilojoules, right? We're looking for Q here, obviously. We're trying to solve for this. Do we have a mass? How much are we trying to heat up, right? So maybe I'll let you guys go ahead and kind of take a look at that. Some of you guys are already writing down numbers, so I don't want to disturb you. You guys go ahead and finish that there if you can. If not, it's fine. I'll help you out in a second here. Obviously, you will need a calculator for this class. Please bring one every day. If you don't have one, please get one. I'm not going to lend out my calculator anymore because I already had one go missing last semester. This is my last one. This is actually my personal home one. So you're not getting it, okay? 750 milliliters of water, okay? Once again, we can change that into a weight. 750 milliliters is 750 grams. But I want my answer in kilojoules. Now, can I put 750 grams in here? Sure you can. Is that wrong? No. Okay? You just have to know what units you're going to get from that. So if you want, you can put 750 grams in here. I'm not going to do that. I'm going to put 0.750 kilograms because as a result, I'm going to get kilojoules as an answer because kilograms and kilojoules goes together, right? So I know I'm going to change this to kilograms right now. That way my answer is done for me already, okay? Can you put 750 grams in there? Sure you can. Okay, and if you do that, I'll show you what you have to do for an adjustment. I want to see units in here as well. So I want to see kilograms. Specific heat capacity, what's C? Specific heat capacity, what are we talking about? We're talking about water. Water is 4.19 joules per gram degrees Celsius. What's the temperature change? We're going from initial to final. So if we think about delta T here, we're going to take the final temperature minus the initial temperature, right? So we're going to take 45.8 here. I'm just going to show you, I know this is kind of silly here, but most of you guys are going to do this on your calculator. 45.8 minus the 15.2. Okay? And when we subtract those two, let's see here. 45.8 minus 15.2. 30.6. Okay? And that's what's going to go into here, degrees Celsius. Okay? Now, once again, I already have kilojoules here, so my answer, of course, will be in kilojoules. Or, so I already have kilograms there, my answer is going to be in kilojoules. Multiply these numbers together, times 4.9 times 0.750, and you're going to get 96.1605 kilojoules. Okay? Now, did anyone use grams? If you did, that's okay. Put your hand up. Great, thanks. Yes. Oh. You did? Yeah. So then he got, of course, 96,160, right? So he got 96,160. That's joules. So then we just have to make sure we answer the question, change it back to kilojoules, right? 3 places over. Should be good, yes? Same answer, obviously, so it's still good. All right, as far as significant digits go here, by the way, we're going to do 3, I think. Are we doing 3? Sure we are, yeah. Okay, so we're going to do 3 based on what we see here, right? So 3 here, 45.8 and minus 15.2, so you're going to have 3 there as well. So you should probably have 3 in the answer. So 96.16, we're going to round that up to 96.2. Okay. On tests, on the diploma, it'll tell you how many digits they want for the answer. Okay, you're going to get lots of practice at that. So you don't need to, for this particular answer, it would say record your answer as a 3-digit number. Okay, 3-digit answer. So you'd put 96.2 in the squares if it was a numerical response question. Okay, so there you go. Good questions? That's easy. Yeah. No? Yeah. Chem 30 is not that hard. Eh? A block of aluminum. Okay. A block of aluminum at 288 degrees Celsius releases 350 kilojoules of energy as it cools down to 25 degrees Celsius. Determine the mass in kilograms of aluminum solid. Okay. So I'll maybe get you guys a little time to set up here. I'll give you a little hint. How's that? Huh? I know, I'm pretty helpful, eh? I'm not going to lie to you. All right, I'll give you a few minutes here, let you think about this. I might, all right, we're going to get going on this one here, just time-wise here. A couple things. First of all, what are we looking for here? Once again, you should be able to solve for variables, yes. It looks like we're determining the mass in kilograms. So probably want to use maybe kilojoules then, if we can. And it's already in kilojoules, so that's perfect. Of aluminum. So we want to find the mass. Well, to find the mass, of course, if I'm going to rearrange this, I'm going to divide by C over delta T and C over delta T, yes? Okay. So really the mass is going to be Q over MC delta T. All right. Now, a couple things here. There's a couple key words that we need to look at here. First of all, Q. It says right here, it releases 350 kilojoules. So that means it's giving off energy. Well, if it's giving off energy, we're going to record that as a negative 350 kilojoules. Okay? And I'll show you, if you're ever confused about this, I'll show you another little hint here. So that has to be a negative 350 kilojoules because we're releasing that energy. Okay? It's not going into the system to heat it up. We're actually cooling it down. We're doing the opposite. So it's going to get released. Okay? C, what's the specific heat capacity? It's aluminum, so we're going to have to look that one up. And then T, of course, here as well. Okay, so what is the specific heat capacity of aluminum there? 0.897. And that'll be in joules per gram degree Celsius, of course, so we're going to put that in there. And the temperature change. Well, remember, it's the final minus the initial. What's the final temperature here? Well, look, it starts at this, and as it's cooling down, it's giving off energy, right? It's releasing its energy. And this is the final temperature here, okay? So if we look at the final temperature and the initial, we have to subtract those two, of course. So delta T here, oops, is the final minus the initial, right? Well, the final's 25, the initial is 288. So when I subtract those two, I get 25 minus 288, which is a negative 263 degrees Celsius. Okay? That's how much energy's basically been lost. Yes? Well, yeah. We're going to put that into here. Okay? Now look, if we didn't have a negative here, you know, a couple things to think about. If you're not sure about this part here, if we don't have a negative here, well, if this was a positive and this was a positive and this was a negative, what's your answer going to be for this little section here? It's going to be negative, right? Can you have a negative mass? No. Okay? So little things like that are things that you need to pay attention to and will kind of help you determine what's actually going on here. Okay? Obviously, a negative is going to make a positive. So what does the mass turn out to be here? Just remember when you do this, of course, make sure you use brackets on the bottom part here. You should get, what is it, about 1.48. And of course, that will be in kilograms, right? Is that what you guys got? Yeah, okay. I have a bad mix-up with the calculator sometimes. 1.48 kilograms. Okay, and how do I know it's in kilograms? Once again, why is it in kilograms? Well, this is kilojoules. Remember, the joules cancel. The grams are going to be left with the kilograms there, and the Celsius cancels. Okay, so 1.48 kilograms in that case. All right, good? Yeah? So got one more here. Piece of tin has a mass of 5 kilograms. It's heated up at a rate of 250 joules per second. The tin has an initial temperature of 27.5. Predict the resulting temperature after 15 minutes of heating. Okay? I'll give you a hint. Okay? When you look at this question, they're looking for that right there, correct? What is the final temperature? Yes? So, if I'm looking for that, I have to know the initial temperature, of course, which I actually do, okay? Its initial temperature is 27.5, so I already know that, that's fine. Also, to know that, though, I'm also going to have to know, since I know this, I also need to know this. So before I can do anything else, before I can find this, I need to find delta T here. To find delta T, basically how much the temperature change is, I need to solve for that over on this side here. So to solve for delta T here, hopefully I'm not going too quickly for you, we're going to take Q over MC. Okay? And get solving for delta T by itself. Okay? If you're not sure about what I just did, well, maybe take a few steps, divide both sides by MC. Yes, cross them out, whatever kind of thing. Get delta T by itself. You need to be able to isolate that. What do we have here? Well, let's see. Q. How much Q are we going to have? Well, it's 250 joules per second for 15 minutes. Well, 15 minutes, of course, we need to change that into seconds first of all. So that's 900 seconds. Okay? So if it's 250 joules for every second, and I got 900 seconds, well, 250 joules per second times 900 seconds is 225,000 joules. Okay? Once again, if you look, this is in kilograms here, this is in joules. Those don't quite match up nicely, so let's change this from joules to kilojoules. So of course that's 225 kilojoules, right? So we're going to put that in instead, 225 kilojoules. Okay? That's going to go there. The mass I'm heating up is 5 kilograms, so of course that's going to go here. And of course we need the specific heat capacity, C, for tin in this case, which is what? 227, okay? 0.227 joules per gram degree Celsius. Okay? So let's calculate that. 225 divided by 5 and, oops, 0.227. I get a temperature change here of 198.237 degrees Celsius. Yes? Good? Okay? So that's my temperature change. Okay? Let's just extend this here a bit here. Once again, that's my temperature change. I need to find the final temperature. So T final minus T initial. Okay. If I'm looking for the final, what am I going to do to get the final temperature by itself? I'm going to add Ti to both sides, right? So add Ti, or whatever you need to do there. I don't really care. But your final temperature here is going to be, your change in temperature plus the initial temperature, right? It's going up by 198 degrees Celsius. If you're starting at, what was it again here? 27 and a half, and it's going up 198, what's the final temperature going to be, right? So, final temperature, what did I say here? 198.237 and 20, what was it here? 27 and a half. So, we add those two together here, and we will get a final temperature of 225.737 degrees Celsius. Significant digits, once again, we're probably going to have to use, okay? So we kind of go back to the question once again. If it's a diploma type question, they're going to tell you, but it looks like 333 kind of thing. So let's go back here with 3, and let's say 226 degrees Celsius, okay? Rounded, etc., etc. That's probably the toughest one, okay, for this first lesson here. Good? Questions? All it is right now, guys, is manipulating the formula, basically finding out what each letter stands for, and plugging in the appropriate values for that, right? Understanding what MC and delta T stand for, okay? And one more here. You could be asked to solve for the specific heat capacity as well. So let's take a look at this one here. Actually, I'm going to get you guys to do this one here. So for this one here, like I said, you want to solve for what's the specific heat capacity. So your final equation here, if you're solving for C, of course, should be, what is it here? Q over M delta T. Okay. Q, it cools down. So once again, it's cooling down, it's releasing energy, first things first, okay, from 80 to 18.5. So we need to make that a negative, cooling down. So it gives off, right, releases, gives off, those are negative values for Q, okay, energy released. So right here, we're going to give you a negative 3.48 kilojoules is what you need to put in there, okay. M here is 87.18 grams of a metal. 87.18 is in grams. Remember, we just put in kilojoules, so we probably should change that to kilograms to make sure those two match up. Okay? Make sure you know that those units go together. That's the biggest mistake with this stuff. Kilojoules, kilograms, grams, joules. Simple. Okay? But you got to remember, they got to match up. Otherwise, you're going to get 1,000 times bigger, 1,000 times smaller. So we're going to here we're going to put in 0.08718 kilograms is the mass that needs to go in there. And then, of course, the temperature change, okay? You're going from 80 to 18.5, so don't forget, T here is F minus TI. 18.5 was the final temperature, and you started at 80. So this, once again, will be negative, of course. Okay, 18.5 minus 80, 61 and a half. Okay, so that there, and just basically figuring that out there. So what do we got here? Negative 3.48 times 3.48 divided by 0.8718 times. Okay, and I get here 0.649, yeah? 0.649 joules per gram degree Celsius. Remember, specific heat capacity is always in joules per gram degree Celsius. It's the kilograms and the kilograms here that cancel each other out. So you're left with joules, grams, degrees Celsius on the bottom, right? Joules per gram degree Celsius along the bottom. So the kiloparts cancel each other out, right? C is in joules per gram degree Celsius. Good? Questions, anyone? Yes, no? All right. I think that's the last one. Was that the same example you guys had? I hope so. Because I've switched a few, and so if they don't match up, let me know, because sometimes I didn't quite make the transfer there. So if they ever happen to not match